Hello, and thank you for watching our demonstration video of the OZ Optics Distributed Strain and Temperature Sensing System, or DSTS. I'm Garland Best, Vice President of Optical Components here at OZ Optics. The DSTS system measures changes in strain and temperature in optical fiber in lengths as short as a few meters to over 150 kilometers. It uses a phenomenon called Brillouin scattering to measure these changes in strain and temperature. The unit is available in two versions, a rack mount version and our newer compact version, which offers the same performance and features in a newer, smaller size factor. Both units consist of two modules. The top module contains the lasers, optics, and electronics to generate the Brillouin signal within the fiber and to detect it. The bottom unit contains a computer which does the data acquisition and analysis so that you can actually see what the Brillouin signal is. To use the unit, you will also need a display, a keyboard, and a mouse. During this video, we will demonstrate how to set up the hardware, how to initialize the system and get a baseline reading, how to measure temperature within an optical fiber, how to measure strain in an optical fiber, how to measure both at the same time and independently of one another, how to make high-resolution measurements over a short distance, how to make measurements in real time, and how to remotely access the system for diagnostic and troubleshooting applications. We hope you enjoy the video and find it informative. Thank you. Alright, so we've set up the machine, the hardware, we've initialized the equipment, we've made a baseline measurement, so let's make some real measurements. Let's start off by measuring temperature. So to measure temperature, we've set up the following arrangement. We have a 200 meter spool of fiber here, we have an 800 meter spool of fiber here, and in between we've got ourselves about 5 to 6 meters of fiber. I have one spool here, just a few wraps, and here we've got wraps around the outside of this canister. Okay, so we'll be showing two different scenarios here at the same time. One where you can actually immerse the fiber into an environment in order to take the temperature, and another one where the fiber is around something and we're going to be monitoring the temperature of the container itself. This would simulate what would happen, say, on an oil pipeline. In these devices, we're going to fill one with ice water and one with boiling hot water and see if we can actually measure those temperature ranges. Okay, so let's put our fiber into our container for measuring the cold temperature. And here we have our container of ice water. And over here, boiling hot water. And now with the water in the containers, we'll start off our measurement process. And the instrument starts recording the values.
So as you can see down here in this window, it is now acquiring the data. What it's doing is changing the laser frequencies step by step, sending pulses through the fiber and looking at the signals being echoed back. From this, it's going to compile all the responses versus time throughout the fiber and do the analysis. As you can see right now, it is so far about 3/4 of the way through the data acquisition. In a minute, it's going to start doing the analysis of all that data. So there, we have finished collecting the data. Now it's starting to do the analysis off the data. It's about 1/4% through. quarter of the way through. Once it's finished here, it's going to show the plot showing the temperature versus distance on the display. We're just about finished. And here's our information. So, if we can zoom in, this is obviously the area where it hit cold, and this is the area where it became hot. We'll put our cursor in the middle here, zoom in a bit, and you can see quite clearly that we have a peak down here about 25 degrees below room temperature, and we have another peak here about 75 degrees above room temperature. So the temperature difference between freezing water and boiling water is 100 degrees C. So this seems to be right on accuracy.
So there you go. That's how you can measure temperature using the Brillouin sensor. I hope you enjoyed this demonstration. Cheers. Now that we've demonstrated how to measure temperature using the DSTS system, let's talk about measuring strain. In principle, the process is exactly the same. The only difference is that instead of selecting temperature for your units of measure, you select relative strain for your unit of measures. And then on your vertical scale, you now see that the unit of measure is strain in terms of micro-unit. Now, rather than just repeat the same process we did before, let's talk about a different measurement technique called dynamic measurement. Now, this method is not as precise as the standard system. It's a little bit noisier, but it has the advantage that it makes measurements in real time. This measurement method is ideal for catching sudden changes such as structural failures in a system, such as a dam or a pipeline. For that reason, we call that feature in our software disaster warning. When you select disaster warning, you're first asked what type of measurement method you want to use. For this demonstration, we are going to pick dynamic measurement. Once you select that, you now confirm that you are measuring strain, and you start by taking a baseline reading, just like we did for measuring temperature in our previous demonstration. We start our laser, and a question pops up asking us whether or not the central frequency is correct. Now, the central frequency is something we set up during the initialization of the unit. So unless something has changed since you initialized the unit, you would normally select yes. After selecting yes, it'll ask you whether or not you want to override the existing baseline in the system. And again, we'll select yes. Once you've done that, it only takes a second for it to create a new baseline in this dynamic measurement process. You are now ready to begin measurements. Again, you select measurement here in the software, start the laser, and the measurement process begins. We'll zoom in so you can see the actual behavior. Now, to demonstrate the strain behavior, we have a fiber attached to a flexible pipe. And we're going to bend the pipe to simulate buckling. Now, as we straighten the pipe, you can see a sudden sharp peak appear on the display, showing our changes in the strain. As we relax the pipe back, the peak disappears. If we bend the pipe again, the peak reappears. So here we're demonstrating in real time the detection of strain on a fiber caused by the flexing or buckling of a pipe.